Okay, let's get started again. So we've discussed atomization. That's the process whereby we're forming the droplets. Now those droplets are going to be interacting with the chamber gas. They'll be decelerating since they were injected at high velocity. And they will also, because of this similar physics to the atomization process, they will also undergo breakup. And so if you look at the literature, drop breakup has been studied for many, many years. Kind of had a resurgence of interest during the rocket era in the 50s and 60s. A lot of work was done to look at droplet breakup. And some of the early theories, again, attributed the breakup of a droplet that's subjected to a high velocity to surface waves growing on the droplet, pretty much like we were discussing for jets. But in the 60s, a new class of theory was proposed, the so-called boundary layer stripping theories. And in this case, the argument was that because of the shear between the gas and the droplet, a boundary layer is developed within the droplet that gets essentially stripped away from the droplet, producing droplets that have sizes that are related to the boundary layer thickness. And then quite recently, in the 90s, Professor Surignano and his group continued this analysis and actually came up with predictions of drop sizes and so on. In my group, we made some arguments that we thought this theory perhaps was not very complete because it relies on shear between the droplet and the gas. And the gas viscosity is very, very low. And in fact, there's no evidence that the gas viscosity is playing a role in the breakup. So we instead proposed a theory called stretching and thinning, which I'll tell you a little bit about. But basically, it's based on photographs of distorting droplets. So we devised an experiment that's shown here, where we had a very nicely designed nozzle that produces a uniform velocity profile. So gas is injected into a chamber at chamber conditions that can be controlled to be high density conditions, for instance. And using a monodispersed droplet generator, we inject droplets into this gas flow and take a look at what happens. So as those droplets are injected from the nozzle, they're nice and round. And as they are impinged upon by this high velocity gas stream, they flatten because of distortion effects. And at low Weber numbers, the droplets basically turn inside out, forming this very thin umbrella shape, which eventually leads to the breakup of the droplets as this very thin sheet breaks up. So that's what's been referred to as the bag breakup regime, and it really only applies to droplets at relatively low Weber numbers. This shows some images taken at much higher Weber numbers. In this case, the droplets are entering from the right and moving left. So here's a droplet before it sees the high velocity gas jet. And right here, you see evidence of the droplet starting to deform. And in these particular images, these were double pulse images. I don't know why it's showing us there. Double pulse images, so you could see the droplet at 2 instants in time. This liquid is flattened out. This liquid droplet is flattened out, and you can see evidence of waves on the surface of this flattened droplet. And a short moment later, you see that those waves have grown to create a very chaotic looking image here. I call this strands of spaghetti, but basically a round droplet becomes these strands of spaghetti. So this is sort of interpreting the picture here. Round droplets become flattened by the dynamic pressure of the gas acting on the stagnation point of the jet. This distorting drop suffers incredible acceleration, going from no velocity in the vertical direction to the gas velocity, which is close to sonic velocities in this case. And this leads to what's called Rayleigh-Taylor instability. The same instability that you see if you turn your coffee cup upside down, right? The acceleration of gravity causes that uniform surface in the coffee cup to be disrupted, leading to the formation of Rayleigh-Taylor waves. All right, so these waves then grow, and essentially because of the, again, the interaction with the gas here, stretch the liquid into these filaments. And on these filaments, you now have the growth of Kelvin-Helmholtz waves like we saw for jets. So one can analyze this. We made measurements of these wavelengths in the pictures here. We did simulations that allowed us to estimate the acceleration of the liquid. And from that, we could calculate the Rayleigh-Taylor wavelengths and growth rates. And they were all quite consistent with what we saw in these images. So for high-speed drops, such as you might see in a diesel spray, we concluded that the Rayleigh-Taylor contribution could not be ignored. And so here's just a summary of droplet regimes that we put together. Basically, what's happening here is the Weber number is increasing. Weber number, again, this is measured using the gas density, right? For a Weber number of about 12, you start to see significant distortion of the droplets, and in the range up to 100, you see that bag breakup that I discussed a minute ago. For intermediate Weber numbers, perhaps the shear breakup or shear thinning breakup mechanisms would be more appropriate. And then finally, what we called catastrophic breakup is for Weber numbers that would be greater than, say, 350. And this would involve the growth, this unstable growth of Rayleigh-Taylor waves. Okay, so that's droplet breakup, and we can include those in our models as well, those regimes in our models. But the other thing that's of interest is the collision between droplets in a spray. Now, when you have a dense spray, the distance between the droplets is very small, and the droplets are also subject to trajectories that are influenced by the turbulence, and so you can have droplets colliding with one another. And Peter O'Rourke, from his PhD thesis, devised a model that's basically still used today with some variations, where he again looked at the kinetic theory of gases and used a very similar framework to predict the collision process in sprays. The idea starts from calculating a collision frequency between the droplets in a parcel. Remember, John Dukovitz's idea is to collect droplets in parcels. The droplets in one parcel with the droplets in another parcel, where these two parcels are traveling at velocity, the droplets in the parcel are traveling at velocity v1 for parcel 1, v2 for parcel 2, and the size of the droplets would be different, but the same in each parcel. So the parcel 1 droplets have radius r1, parcel drop 2, and parcel radius drops 2 in parcel 2. So the collision frequency depends, and we're talking about the collision of the N1 droplets in parcel 1. The number of collisions with the N2 droplets in parcel 2 depends on the collision cross-section, the cross-sectional area that's swept out by these droplets, and the relative velocity, the volume that is occupied, in this case the cell volume for our calculations, and a collision efficiency term. It turns out that this collision efficiency term is of the order of unity, and many of the models assume that it's 100% efficient. But basically, if you look in the literature for impacting droplets on surfaces, you find that depending on the size of the droplets, if the droplets are very small, they can actually bypass larger droplets, or if you inject droplets at a flat surface, flat plate, they can get caught in the boundary layer and not even impinge on the plate. So that's accounted for through this parameter k here. But for the sprays of interest that we're discussing, for instance, in a diesel or gasoline direct injected spray, this is typically chosen as unity. Okay, so this is the construct of the model. Now, because this spray model of Dukovitz is a Monte Carlo approach, stochastic model, the idea here is instead of using deterministic theory to figure out the number of collisions that occur, to treat it as a random process, a Poisson process. In that case, one can show that the probability depends on the collision frequency, the time interval between successive collisions, which in our case would be the computational time step, and the collision frequency. And this gives you basically the number of events that would occur, or number of collisions, and the probability of that number of collisions. So in accordance with this stochastic concept, you choose a random number between 0 and 1. That gives you the left-hand side. You know the collision frequency, you know the time step, so you can find n, where n is the number of collisions between drops in parcel 1 and drops in parcel 2. So that was his idea, and it was a very successful idea that has been widely used for modeling collisions. So let's say that two droplets collide. What happens to them after the collision? So here's the larger droplet moving along a certain trajectory. Here's the smaller droplet moving along its trajectory. And the two droplets collide. So depending on the orientation of these trajectories, one can define a parameter called the impact parameter, which basically measures the distance between the centers of the droplets at the moment of collision. And so here, B is the distance between centers relative to the relative velocity vector, and the size of the droplets. The delta here is the ratio of the droplet sizes, the diameters, in the small drops and the large drops. And here's our Weber number again, based on the liquid density and the relative velocity between the droplets. Surface tension appears here, and the diameter of the smaller droplets. Okay, so here's the impact parameter. If the impact parameter is 0, the two droplets collide head-on. If the impact parameter is 1, they just slide past each other. And experiments show that depending on the Weber number, one sees different outcomes. So for example, for the head-on droplets, if the Weber number is sufficiently high, the droplets basically bounce off each other as though you had taken a tennis ball and bounced it off a surface, right? So that's called reflexive separation. Up here, there's another regime that also is called bounce, but this is where the droplets kind of slide past each other, all right? Sometimes that's referred to as a grazing collision. So in between these is the stretching separation regime. And so here's a picture that we took in our lab showing two monodispersed droplet streams, in other words, drops of the same size, colliding with one another to form a pair here. And then the pair separates due to surface tension and inertia effects, producing basically a stream of droplets in between the two parent droplets that had collided. So this would be the stretching separation regime. The green data shows what happens when coalescence takes place. So the two droplets collide, and instead of bouncing apart or grazing each other, they actually combine to form a single coalesced droplet. So here's a picture of that from NASA Ashgriss's paper, very interesting paper. The droplets are moving in space here from the right to the left. What he did was, I think this was just water, he colored one stream of droplets red and the other he left transparent. Here is a case where the impact parameter was about 0.5, so we're in that coalescence regime. And you can see that the droplets merge here and form a single droplet that basically remains intact. Why is this the case? Well, surface tension is what's pulling this liquid mass, this combined liquid mass, into a nice round droplet. The opposing force is the rotational energy. If these droplets are rotating such that you have a centrifugal force acting against that surface tension, the droplets will not coalesce, but will again separate in the separating collision case. So in the model, what one does is these parameters on the right-hand side are known for every droplet. Delta is the ratio of the size of the two droplets. Weber number is calculated knowing the velocity of the droplets and its size and so on. Calculate the right-hand side and then choose a random number between 0 and 1. And if it's greater than the parameter on the right-hand side, you argue that you had coalescence. So that's how it's done in the simulation. Okay, the other option is to have the grazing or separation that you saw in the picture I showed you previously. So here you have the combined droplet pair. You can see evidence of the rotation. Now the red is at the bottom and the white's at the top here. This mass is rotating and stretching apart and eventually produces two droplets. So basically, nothing has changed here. You had two droplets that became two droplets. And pretty much the red is down below and the white is up above. So this is basically a grazing collision that you might see in such a simulation, that you would include in your simulation. The reflexive separation is, as I mentioned, the tennis ball bouncing against the surface. Here you have the two drops moving together, forming temporarily a unified liquid mass. There's a lot of interesting physics associated with bouncing of the liquid and basically separating out to form basically the same pattern that we had when we started. Notice the impact parameter is very small in this particular case. It turns out that the regime boundary between the coalescence and the reflexive separation is a function of the ratio of the sizes of the drops. And so that's accounted for here through a set of parameters, again with a random number chosen to give you the impact parameter. You determine that you're in this reflexive regime, calculate the parameters to see if you lie above or below the line. Okay, so that's the collision model. And so the droplet breakup, the droplet collision and coalescence, the droplet atomization are all part of the spray models that I will be talking about more in the next part here. Lagrangian drop, Eulerian fluid, discrete droplet models. These are the workhorse models these days for commercial codes and for codes that are widely used to simulate two-phase flows. Also used in the Fluent code and various other commercial codes. Detailed models are available for use in CFD models to describe the effect of the nozzle, the injector nozzle, the liquid and gas properties, and so on, and the drop breakup physics. I tried to describe some of them today. However, because sprays are so ubiquitous and so important in applications, obviously there's a lot of research still needed to totally become predictive. And so you'll see a huge amount of experimental and modeling work through the Institute for Liquid Atomization and Sprays. There's a worldwide organization, but there's an American section as well. And conference papers, the Atomization and Sprays Journal, and other places. Also, a lot of work being done using large eddy simulation and DNS spray modeling, as I mentioned, with Mario Trujillo in our group. And we're really starting to understand more about the physics of what happens, how these waves grow to produce droplets in a practical spray. This wouldn't really be possible without a lot of experimental input, so there's a great deal of interesting work being done, for example, in Sweden, looking at ballistic imaging of sprays that allow you to actually probe through the dense spray core and see the structure of the spray, the X-ray imaging that I mentioned. A lot of work in trying to include the effects of turbulence through LES and DNS as well. Questions about this? Yeah. Yeah, so what you're saying is that there's no Reynolds number on this plot here. So actually, my student Achuth Munanur has an International Journal of Multiphase Flow paper where he discusses the effect of viscosity on these satellite droplets, and that's actually included in the models that we use. So viscosity is very important. You know, that's these little drops you see that are formed during the stretching process depend a lot on viscosity. Pressure, I'm not sure what you meant by that. The gas density is important. Yeah. However, for these models, the gas density really is thought to only appear in the effective velocity because the droplets are going to decelerate. The droplet velocity will be determined by the gas density. And so it only appears implicitly over here. Yeah, so there's, in Achuth's paper, he mentions that a little bit here, but that's really not included in many of the models that I've seen. I know Professor Law has some very interesting models that account for the gas trap between the colliding drops. But usually, most of that's down here at quite low Weber numbers. And, you know, for diesel sprays, we're interested in relatively high Weber numbers. Yeah.
I'm just curious, you effectively decouple the drop size from the airstream velocity. But there's, when you're injecting at diesel condition at 1,000 bar, the drop has some history of internal velocity and internal motion. And none of the modeling seems to be capturing any of what might be happening inside of the droplet. Is anybody thinking about that? Or is that affecting evaporation rates?
I'll talk about that next with vaporization. But for atomization, I don't know of anyone who looks at it at that level. Yeah. Yeah. Okay. All right. So I think I'm done with the first part. Let's move then to the second part. Okay, so we're going to now talk about droplet drag, wall impingement, vaporization, and some spray modeling. So at the Engine Research Center, as I mentioned, we've worked for some time on spray model development. And the concept that we use is the Lagrangian drop Weyerian fluid idea. We introduced something called the blob injection model, which makes it relatively simple to apply these models. The idea here is that the liquid is injected through a nozzle whose dimensions are included when one calculates the cavitation process. But instead of a continuous liquid, we inject what we call blobs of liquid that basically are large diameter droplets, if you like. And those droplets then undergo breakup using the theories that we've discussed, the Kelvin-Helmholtz and the Rayleigh-Taylor breakup. The idea would be that really in this region, a continuous liquid or blobs of churning liquid would be very difficult to distinguish anyway. So why not use the construct that's already there for tracking droplets to represent the injected fluid? So that's the blob injection model. So in a certain region, remember we discussed the breakup length. We know that we'll have primarily injected fluid, continuous fluid, if you like. Here we use the Kelvin-Helmholtz model to look at the wave development on each of those blobs. And downstream of this, where we expect the liquid core to end, and we would have only droplets, we then combine that with the Rayleigh-Taylor model, because now these droplets are no longer traveling at the injection velocity, but are decelerating because of the ambient gas, the high-density ambient gas. So we expect Rayleigh-Taylor instabilities to play a role. So that's now combined the discussion of our previous section here. Once these droplets are formed, they undergo breakup and collision and coalescence. And so we can track the droplets as they penetrate into the combustion chamber. They are exchanging momentum with the gas. That's where the droplet drag comes in. And then they are also vaporizing because the entrained air is high temperature gas, leads to the vaporization process. And eventually they can impinge against the surfaces of the piston in this example here. So we have to worry about spray wall impingement. So this is how the models are actually introduced. So let's discuss then the momentum transfer between the injected liquid and the gas phase. So remember that term F that we discussed in the generalized equations for the Lagrangian drop Eulerian fluid model. This would be the drag force per unit mass. And if you look in the fluid mechanics book, you can see that for flow around a sphere, you can identify the Stokes viscous drag. Here's the gas density. You can identify added mass effects. This really only applies to bubbles where you have to basically move away a volume of the surrounding fluid equal to the volume of the droplet. But since the gas density is very low, in the case of droplets being injected into a gas, this term is generally quite small. But for gas bubbles injected into a liquid, this is a dominant term. And then you have a term that involves the boundary layer development on the sphere, the so-called Bassett term. So one could, in principle, keep all of these terms, but in practice, what is done in most codes is to say the mass, that's the density times the volume of the drop times its acceleration, can be determined from the dynamic pressure, which is basically the gas density times the relative velocity between the drop and the gas squared, times the frontal area of the droplet, times a drag coefficient. This thing here just gives you the direction of the vector that is going to be oriented in the direction of the relative velocity. Okay, so the drag coefficient, well, it depends on the Reynolds number. And here the Reynolds number is based on the gas phase viscosity, all right? For low Reynolds numbers, we use basically the laminar flow or Stokes drag part of the drag coefficient. Whereas for high Reynolds numbers, we use the turbulent drag coefficient, which is basically just a constant. So that's how the drag coefficient is calculated, and hence the acceleration or deceleration of the drops. However, I mentioned that the droplets also can distort. And in the Kiva model, the TAB model was introduced originally based on the Taylor analogy breakup idea, where G.I. Taylor argued that one way a droplet can break up is because it's subjected to this pressure force at the stagnation point, it flattens. And if it flattens sufficiently, eventually you could argue that it's going to be broken up into smaller droplets. So the flattening is determined by this parameter y. And here is the ordinary differential equation that you can derive by looking at the force balance on this spherical droplet that's subject to a compressive force due to the dynamic pressure. It involves the liquid viscosity, the surface tension, and then the forcing function, which is the relative velocity squared, the kinetic effect, dynamic pressure effect on the droplet, and then the droplet radius. So what is done in the code is this equation is tracked or solved for every droplet or every droplet in a parcel of drops, so you only have to do it for each parcel. And you keep track of the distortion. Well, it turns out that you can also use this to determine the drag coefficient on the droplet, because the drag coefficient for a sphere is actually less than the drag coefficient for a disk in this orientation by the amount of 3.632. So when y is equal to 1, you have a disk. we increase the drag coefficient up to the value of the drag coefficient for a disk. And in between, when y is 1, we use the drag coefficient for a sphere. So in this way, you're able to keep track of distortion of the droplets. So the other interesting effect that is seen in a practical spray is the dispersion of the droplets. So you inject a bunch of droplets in a certain direction, and what you'll find is they will basically separate out and disperse. And that is modeled using the Monte Carlo method that's based on the turbulence field. And this was introduced by Geisman some years ago. The idea here is that we have the gas velocity, which is the mean velocity, plus the fluctuating velocity due to turbulence. So one knows that the turbulence, or assumes that the turbulence can be expressed in terms of a Gaussian distribution function, where the width of the distribution function depends on the turbulence kinetic energy, K. So at any time, one can basically, given the turbulence kinetic energy, draw from this distribution function to determine the fluctuating velocity component. Okay, so why is that important? Well, the droplets are going to be moving in a turbulent flow, and depending on a parameter called the Stokes number, they are either going to be unaware of the turbulent eddies, or they're going to become trapped in those turbulent eddies. So if I have a measure of the turbulent eddy size or time scale of existence, and I know the characteristic time that that particle spends in that eddy, I can determine the Stokes number. So in Geisman's approach, he looks for what he calls the drop eddy interaction time. The eddy lifetime, T sub E here, it depends on the eddy size, and we know how to calculate the length scale of an eddy, and the U prime, which is square root 2/3 K. So this is the lifetime of an eddy, and I compare that against the residence time of a droplet in an eddy, which is basically the size of the eddy divided by the relative velocity between the droplet and the gas. And then I choose the minimum of those two time scales as my interaction time. When this time has elapsed, I go back to my distribution function and I choose a new random velocity, because now the droplet has moved to a new eddy. And this process then, because of the random perturbation that's applied to the droplets in calculating the drag forces and therefore the trajectory, scatters the droplets or disperses them. Notice the Stokes number is the ratio of these two time scales here. If you have a very large Stokes number, that means that the residence time in a particular eddy is very small. The droplet just passes through those eddies like a cannonball would pass through a flow. Whereas if the time scale is such that the residence time is very large, that droplet becomes trapped in an eddy, and it will remain in that eddy and be subject to its flow longer. And the result of that is that its trajectory will be influenced, especially for intermediate Stokes numbers of the order of 1. So that was an interesting development. Okay, so we've discussed droplet drag. Let's talk now about spray wall impingement. So those droplets that are in our spray, they've been breaking up, they've been undergoing drag force, the influence of drag forces and dispersion, eventually might reach a boundary. And if you look in the literature, you'll see that this is a widely studied phenomenon. But basically, droplets can either bounce off a wall, or they can spread along the surface of a wall. There are actually other regimes that I'll talk about in a minute as well. But the parameter that is useful here to monitor is the Weber number based on the normal component of velocity. So this droplet has a normal component, U sub n. And the Weber number that's tracked then is on this axis, the incoming drop Weber number. And the outgoing drop Weber number, that's after it's collided with the wall, is on this axis. And what you find is that for low values of Weber number, the droplet bounces off along this straight line trajectory here, elastically, like your tennis ball bouncing off a hard surface. However, as you increase the Weber number, you see losses occurring because of distortion of this liquid, surface tension playing a role here as well. And so you don't recover the full kinetic energy of the impacting droplet, but instead you see eventually the rebounding droplet has zero normal velocity, and it spreads along the surface of the wall. So this is some experimental data from Wachters and Westerling many years ago. So we used that experimental data to produce a model for droplet wall impingement that basically looks at several different regimes. At very low Weber numbers, when you spray droplets on a wall, they stick. If this wasn't the case, you wouldn't be able to paint anything. Okay, so very low Weber number, droplets will stay on the surface. For intermediate range of Weber numbers, the droplets reflect off the wall. And as I said, for high enough Weber numbers, the droplets basically slide along the wall. So if you've ever squirted a hose at a surface, you'll see that the liquid flows in the form of a film on the surface in all directions. So we developed a model where we tracked the height of the film, considering a continuous liquid flow. And we argued that if the droplets that were approaching the surface were sufficiently dense, it would behave pretty much like a continuous liquid jet. And the film thickness could be interpreted as the probability that the droplet would be traveling in a particular direction. So here I'm showing that as I incline my jet at angle alpha, I'm going to have a thicker film in the jet direction versus in the direction against the jet. And if I look at a plan view of that, what I can represent this as is in terms of an azimuthal angle, capital phi here, is the probability that the liquid will be traveling at a given angle phi. So from an analysis of this problem, we showed that the angle that the droplet would leave the impingement point at is determined by this parameter beta and a random number, in, again, consistency with this idea of a stochastic model. We choose the random number between 0 and 1. For a given beta, that gives you the angle at which the droplet is going to leave the surface. Beta here is determined from this equation, and it's related to this angle of approach, alpha here. So the analysis is shown in this reference. So that's a model that we've used quite widely for wall impingement modeling over the years. And it allows you to look at configurations like this one here. We devised an engine setup where the piston featured a step or a pedestal. Here was the injector. It was a single-hole injector that injected onto the pedestal. The sprays were then formed by the droplets sliding along the surface and then leaving at the edge of the pedestal and penetrating into the combustion chamber. We made measurements of the radial penetration, that's this distance, as a function of time for various conditions, and basically tuned our models to produce these, to match the experimental data. So one of the things that we also noted in this exercise was that the droplets, upon impinging on the surface, are destabilized. And you can imagine that that would be the case, right? This is quite an impact on a droplet to hit a surface. And so I mentioned that we had model constants that allowed us to calculate the breakup time of a droplet. What we found was that we had to reduce the breakup time of the droplets to account for shattering of the droplets as they impinge on the surface. So for the free jet here, the breakup constant was relatively large. That enabled us to calculate the free jet breakup fairly well. But then after impingement, we found we had to change that breakup constant to account for the enhanced breakup, reduce it significantly. So this again is a sub-grid scale process that we've been discussing for all of these models. And some recent work that we just have published or about to publish in Atomization and Sprays looks at a different way of treating the wall interaction. that I think is a little bit more grounded in reality, because we use analytical solutions, like we do with heat transfer, where we use the law of the wall. Here we use a wall jet model. So the idea is this. Droplets impinge on the surface, and there are well-known criteria that tell you whether that droplet is going to splash if it encounters a film of existing liquid on the surface, depending on the film height and the diameter of the droplets, and also the Reynolds number of the fluid, in other words, the viscosity of the liquid. So we use this to determine if a droplet is going to splash upon impinging on the surface. Some of that liquid will remain in the film, and some will then be splashed. The amount that is splashed is given by another correlation that we obtain from the literature, which again depends on the film thickness, the diameter of the impinging droplet, and a coefficient here that essentially accounts for the Weber numbers of the droplets. So this is kind of an empirical input to the model. So once the droplet is argued to splash, it's now lifted up off the wall, and we calculate its trajectory using the same drag formula that we showed before, except there's an additional term here, the so-called Safman lift force. If you look in the literature, the Safman lift force is really a force that is a result of a gradient in velocity across the droplet. So basically, you can think of this as a spinning of the droplet that lowers the pressure on one surface of the droplet versus the other, and then imparts a force, in this case a force normal to the wall, on the droplet. And this has the effect of lifting up the droplets and causing them to form a vortex, which is, I'll show you in a minute, seen also in experiments. So here's our computational cell. All of this stuff is occurring way below the resolution of our simulation. In the literature, there's a celebrated paper by Goddard where he predicts the velocity profile in a gas jet that's impinging on a wall. Remember that these sprays are fairly dilute by the time they reach a wall, so it's not a bad assumption to use a gas jet analysis to represent the gas flow. If you look at the CFD predicted velocities, that's these blue vectors here, they are much, much smaller than would be seen if you were able to resolve this entire region, because the momentum is spread over such a large area in your coarse mesh. So instead of using the CFD velocity, we use the velocity from the Goddard analysis to calculate the relative velocity between the drop and the gas. And we use the profile, which is measured as a function of distance from the wall, to calculate the velocity gradient. So that's kind of a way of interacting, producing a subgrid scale model that allows the drops to interact more faithfully with the physics close to a wall. So here you see some simulation results compared with experimental results. Experiments are shown here. The main thing I want to show here is that the penetration of the jet impinging on the wall, the penetration distance R here, is quite well captured by the simulation, as is the height here. I think I can show a movie here that shows this simulation. And you can see the formation of this droplet cloud, and during the movie you probably were able to notice this roll-up of this vortex at the head of the jet. So if you didn't use this model that we just discussed, what you find is that the predicted wall jet radius is a function of the mesh size. And only when you have very, very tiny meshes near the wall of the order of 1/4 of a millimeter are you able to match the experimental data. But with this new model, we find we can match the experimental data all the way out to 2 millimeter meshes, almost. I mean, there's a little bit of an error here, but basically much less grid dependence by introducing this subgrid scale model that allows you to predict the movement of the droplets in the neighborhood of the wall. So we think that's a useful addition. This shows the performance of the model over a range of other conditions. Here we're looking at ambient pressure effects from 5 bar to 15 bar, again for a variety of different mesh sizes near the wall. And you can see the results are pretty insensitive to the mesh size. So any questions about that before I move to vaporization? Okay, yeah, there's one. Absolutely, yeah. That's what I do for a living. So we have, for example, Society of Automotive Engineers papers that describe exactly that. They tell you what are recommended values for constants. The constants are typically chosen out of engine using experiments, for example, from Sandia, where they have constant volume bomb or vessel experiments looking at just the spray. We match the spray in that condition, and then we use those constants when we go to an engine with a similar injector arrangement. So yeah, that's a very important part of all of this. The alternative, there isn't an alternative. You just cannot resolve these processes with a practical calculation that an engineer can use in a reasonable time. Any others? Yeah. Sure, thanks for that question. Yeah. So the question was, is the wall temperature involved in these spray wall impingement cases? Indirectly. I'm going to be talking about vaporization now, and that also includes vaporization of liquid films. In the models, the liquid films are treated as though they were droplets, and so there is a heat transfer from the gas phase to the liquid film, and then in turn heat transfer to the wall. So that is something that we do include in our models, but I have not discussed that yet. Okay, so droplets in a high temperature environment vaporize, and the vaporization process is pretty well understood. There's, for example, Bill Sirignano's textbook describes this in great detail, and there are a bunch of, Ed Law did a whole lot of work in droplet vaporization. But basically, here's our droplet. There's the possibility of internal circulation. We brought up that issue a minute ago. Inside the droplet that is basically stirring up the contents of the droplet. We're interested in what happens at the interface between the droplet and the environmental gas. One can have equilibrium processes where the, let's say, fuel molecules in the vapor phase can recombine with the liquid or go in the opposite direction when you vaporize. Generally, most models assume an equilibrium process at the surface, thermodynamic equilibrium. So we can characterize that knowing the vapor pressure as a function of temperature at the surface. We are interested in mass transfer and heat transfer, again, between the two phases. And this droplet, of course, is undergoing relative motion, so that leads to those circulation currents that I discussed as well. What we are interested in is knowing the conditions at the surface of the droplet and the conditions at infinity or far away from the droplet, which the difference between them is essentially the driving force that leads to the vaporization process. So for single component droplets under low ambient pressures, the droplet vaporization model is very well developed and leads to the so-called d squared law. The droplet surface area changes linearly with time. And that's reflected in the vaporization models that are standard models in many commercial codes and also in the Kiva codes, the open source codes. So here's my droplet. It's in a computational cell. Droplet radius R here. The mass fraction of species 1, whatever that may be, one component of the fuel, for example, at the surface is Y1 star, and its mass fraction in the computational cell is just Y1. The difference between those two is the driving force for vaporization, and this is Spaulding's mass transfer number that appears in the equation for the rate of change of radius of the droplet that we discussed earlier. Other parameters are the diffusivity. In this case, this would be the laminar diffusivity for diffusing mass away from the droplet, and the Sherwood number. Sherwood number basically measures the effects of convective flows, which would accelerate the vaporization of the droplet at high Reynolds numbers and Schmidt numbers. The fuel mass fraction at the drop surface is calculated from our thermodynamic tables, knowing what the vapor pressure is at the surface as a function of drop temperature. Here you have the molecular masses of the participating species. So this is the standard droplet vaporization model, the so-called Froseling correlation that's used in a number of codes. And, I should just have pointed out, it leads to the d-squared law, because if everything is constant on the right-hand side, you can bring this radius over here, and you have r dr dt is a constant, which is r squared, right? dr squared dt is a constant, giving you the r squared law or d squared law. So the droplet is also undergoing heat transfer. So here you have your droplet at temperature Td, and here we've assumed there's just one temperature characterizing that droplet. The gas temperature is T infinity, so the driving force is that temperature difference. Here the Nusselt number is important. You saw Sherwood number for mass transfer. Nusselt number here, again, is a function of the convective flow conditions through the Reynolds number that measures the relative velocity between the drop and the gas. Here, if you look at the conservation equation, essentially we have the mass of the droplet, the density times its volume, the specific heat of the droplet, the rate of change of drop temperature with time, and then the source terms would be the latent heat of vaporization, which depends, again, on the droplet temperature times the rate of change of droplet volume. And then on the right-hand side, the terms involving heat transfer from the gas phase to the droplet or from the droplet interior to the droplet, but that only applies if there are differences of temperature between the drop and its surface. But for the standard model, the only heat transfer that you would consider would be from the gas to the droplet, Q sub D here. Okay, so that's to heat up the droplet. So when you inject a droplet, it's at a certain temperature determined by what happened in your injection system and so on. Then it encounters the high temperature gases in the chamber, and that's what drives the heat transfer, heating up the droplet. When the temperatures rise sufficiently, you start seeing the mass transfer. Of course, in reality, droplet vaporization is more complex than I've just described, and there are a number of regimes. And really, in order to track these, you need to distinguish between a droplet temperature and the surface temperature of the droplet. So in more advanced models, such as we use in our version of the code, we have formulated models that allow you to deal with normal vaporization or evaporation from droplets that are heated from the environment, like we just discussed. So here the drop temperature is less than the temperature in the gas. The surface temperature can be less than the boiling temperature, so this would be just your normal vaporization of a drop here in the room. We can also have evaporation cooling. So in this case here, the ambient temperature is less than the boiling temperature. The surface temperature is lower than the drop temperature because of the latent heat effect at the surface of the drop. We can have boiling heating. So in this case, the droplet temperature is less than the boiling temperature, which is equal to the surface temperature. And here you have a hot environment that's causing the boiling. And then we also can deal with flash boiling. So in this situation, droplet temperature is higher than the boiling temperature and the environment temperature. So you have basically superheating of the droplet since the surface temperature is less than the droplet temperature. and the environment temperature is what's driving this process. So this would be flash boiling. So these are all regimes that are of interest in actual engine applications. Yeah? Sure. Sure. So the question was, what happens when the droplets become really small? We throw them away. Basically, they have very little mass. You know, the mass goes as the radius cubed. So when the droplet size reaches a fraction of a micron, the amount of mass represented there is very, very small. And you can convert that directly to the vapor phase. The other thing is, let's say I use the d squared law for such a small droplet. I find that its vaporization rate is extremely high, and it will disappear in nanoseconds anyway. So we don't track them. We do use those ideas, though, for the soot particles, Smirnowski equations. Yeah. Okay, here are the vaporization models that we currently use. Here's our droplet. It has two temperatures, the drop temperature and the surface temperature. We're interested in heat transfer not just from the environmental gas, but also heat transfer within the droplet. This allows you to take care of the superheated drop situation. Basically, we have two equations, the energy balance and the mass balance. The first term on the left here, okay, so here's the mass vaporization rate times the latent heat at the surface temperature. First term on the right-hand side represents the difference between the drop temperature and its surface temperature times an effective heat transfer coefficient. And there's another term over here that is basically driven by the difference between the temperature in the gas and the surface temperature. It's a little complicated, but this equation also accounts for the mass transfer number, the difference in mass fraction of fuel at the surface of the drop and at infinity, far away from the drop. Mass balance, we have the mass transfer term here and Spaulding's transfer number. So that's for normal evaporation. For superheated drops and boiling evaporation, we modify this equation because now the surface temperature equals the boiling temperature in both of these terms. And the surface mass fraction is equal to unity, right, because you have boiling. So we modify the equation as shown here. The other thing that we do is we introduce an empirical correction to the effective heat transfer coefficient that accounts for basically bubble formation in the droplet, in the superheated droplet, as a function of the degree of superheat. So for a given, this is a curve fit here, for a given amount of superheat, we modify the heat transfer coefficient accordingly. So basically, these models try to incorporate as much of the physics as you can. One other thing that I didn't mention here was how we calculate the heat transfer coefficient. It depends on the conductivity of the droplet and the thickness of the boundary layer between the surface and the drop interior, which we assume grows with time according to some effective diffusivity. And there was a question earlier about, what happens to how do you account for movement of the fluid inside the droplet? That's where this effective diffusivity comes from, or comes in. Especially Bill Sirignano and his work has shown how you can estimate this mixing, interior mixing of the fluid inside the droplet and arrive at effective diffusivity. We use that then to determine the growth of the boundary layer, which then affects the effective heat transfer coefficient. Okay, all right, so you've got the basics of a vaporization model. What fuel are you going to use? Well, we're interested in real fuels, gasoline, diesel. So if you look at how you can break down the components, you have thousands of components in practical fuels. You can break them into these various classes, normal and isoparaffins, naphthenes, aromatics, olefins. And in fact, you can see that they are distributed widely over a range of carbon number in the molecules. For example, the aromatics shown here in the purple, the isoparaffins, normal paraffins, and so on, for gasoline. If you look at diesel fuels, again, you're going to have aromatics, paraffins, naphthenes, olefins, relatively small number of olefins compared to gasoline, and so on. So how are you going to incorporate all of these constituents in your model? The approach that we use is actually 3 different approaches. The first and simplest is to say, well, I'm going to just represent gasoline, for instance, with one single component. So here's my actual distribution of, if I sum up all of these distributions here as a function of molecular weight, I'm just going to say pick something in the middle and represent gasoline with isooctane. And that's widely used, that approach. A single surrogate species to represent a fuel. Maybe you'll use N-heptane or tetradecane or something for diesel fuel. The next approach is to say, well, I'm going to sum up all of these constituents, produce a distribution curve in terms of the derived molecular weight, and fit this distribution curve with a distribution function. And this is called the continuous thermodynamics approach, which has also been used to represent a realistic range of molecular weights in the fuel. And I think the more recent and more popular approach, now that we have more computer access, is to consider what's called the discrete multi-component approach. The idea here is that each class of compound is represented as a discrete component. So instead of just having one component representing the fuel, you'll have as many as 20 or 30 components that you track as part of the fuel. So the difference between these approaches basically boils down to bookkeeping. For the continuous multi-component approach, the liquid phase is described as with a distribution function in terms of a variable which could be the molecular weight. You have to specify the form of this distribution function. The oil companies and so on have done this and have produced these distribution functions that have parameters that describe the width and the center location of the distribution function as a function of molecular weight. Those are used then in these models. So the vapor phase would be calculated from moments of the distribution function, and one would then introduce those moments into the gas phase equations. So that's one approach. The discrete multi-component model basically doesn't differentiate between the gas phase species and the liquid phase species, but instead says I'm going to have all of them represented as individual species in my calculation, some of which will be appearing in the droplets as liquid phase, but they will also appear in the gas phase, same species. So I can represent that as a delta function for each species in terms of its molecular weight, and just keep track of the mole fraction of each species in each phase. So in that case, you have a vapor phase transport equation for each species, and particularly when they leave the liquid phase and enter the gas phase, that will appear as a source term in the vapor phase transport equation. If you sum over all of the fuel species, you'll basically have one equation that represents the rate of change of fuel mass fraction. But we will actually track each of the components. So here's some simple models that we've looked at for 2 different diesel fuels, a narrow cut and a Euro diesel fuel, where you can represent the diesel fuel using this discrete multi-component model with 4 species for the narrow cut case here, and 6 species for the Euro diesel. What are these species? Well, they range from tetradecane to octadecane here for the narrow cut diesel. Here we have tetradecane. We even have an isoalkane here, and up to the octadecane. So given a particular fuel, if you know how to choose the surrogate components, you can represent the molecular weights just like we did when we discussed the continuous distribution, which would be the red lines you see here. But now we're going to track each of these components separately. So basically that adds 6 partial differential equations to your model, because you need 1 partial differential equation to track each of the species. And just to show an example of that, this is a diesel engine with early injection of a fuel with a mean molecular weight of 200 here. This is for that Euro diesel fuel. After the fuel has been injected and vaporized, you can plot the fuel molecular weight distribution in the chamber and identify that at this location, you have more of the heavy ends, whereas at this location, you have more of the lighter ends. And in that way, you can actually track where each of these components would be in the combustion chamber. Why is this important? Well, we know that the ignition depends on the molecule, the fuel molecule, right, in our combustion model. And so, for instance, the ignition delay associated with heavy alkanes is going to be shorter than the ignition delay associated with light alkanes. So I would expect, looking at this plot here, that ignition is going to occur somewhere over here because I have more of that heavy alkane in that location. So the discrete multi-component model basically allows you to make a prediction of where the fuel is most likely to be more reactive. And this is even more obvious when you look at gasoline, because gasoline has a wide range of components, going from very light components, this would be isopentane here, to dodecaine. And if you do a calculation with the, 7 species? 1, 2, 3, 4, 5, 6, 7 species. This is for gasoline injected through a 300 micron nozzle at 100 meters per second, and we're looking 2 milliseconds after the start of injection. Those droplets are vaporized. And what I see here, if I look at the molecular weight at 2 points in the domain, near the head of the spray, we've got the heavy components that took longer to vaporize, and so we see a distribution that's kind of biased towards the heavy molecules. Whereas nearer the nozzle, where the more volatile species vaporize first, you see them showing up. So there's no combustion here. The question was, is there combustion going on? No, this is just vaporizing. We're just looking at the vaporization process. And we're seeing that the volatile stuff comes off first, right? Which is what you'd expect. Absolutely. So the combustion model will take a look at this distribution in each computational cell, and it will perform depending on the mechanisms that you use and so on. And in this case, probably if this was going to self-ignite, if this was a compression ignition, it would be occurring out here where the larger alkanes are located. For gasoline, yeah, so we have a number of I'll talk more about that, but it depends on your choice of surrogates. This was just an example to show that you could keep track of them. But yeah, I'll talk more about that in a minute. Okay, so I spoke about the vaporization model and the assumption that we have thermodynamic equilibrium at the surface of the droplets. That's a good assumption. However, it turns out that if you have a mixture of components in your fuel, and some of those components are polar, like alcohols, you have interaction between the molecules in the liquid phase that can suppress the vaporization in some cases, or can even enhance vaporization in other cases. And so there's a model that has been developed called the UNIFAC model that allows you to correct the standard thermodynamic model to account for this effect through what are called activity coefficients. So here's the mole fraction of our component I in the gas phase. Here's the corresponding mole fraction of component I in the liquid phase. And these two are related through Raoult's law in the case of ideal mixing through the vapor pressure and the ratio of the vapor pressure to the total mixture pressure. So that's our standard equation. But now, in the UNIFAC model, you introduce this parameter gamma, activity coefficient, which consists of two parts, as shown here, a combinatorial and a residual part. The combinatorial part basically accounts for differences in the sizes and shapes of the molecules. The residual part accounts for energy interactions between the functional groups. So here's, let's see, this is ethanol. It has an OH functional group, it has a CH2 functional group, and a CH3 functional group. The activity coefficients for each of these functional groups are stored in a table. And knowing how your fuel is made up, you can then determine what this activity coefficient would be for that species. And the number of functional groups are then related for the total mixture to give you an effective overall activity coefficient. So just to give you an example here, we're dealing with cyclopentane, toluene, ethylbenzene. This is a gasoline surrogate mixture that we've looked at in a certain mole concentration of each of those species. This is what the molecules look like here. If you go into the UNIFAC database, you can identify, using the construction of the molecule itself, what those functional groups would be. And then from those functional groups, determine those activity coefficients for each of the components. So basically, you're multiplying the vapor pressure determined for each of these species, which would be in the absence of all the other species, by a correction factor that accounts for the other species. So this is an important, it can be an important effect. I'm just showing a simple example here with E10. So this is 10% ethanol in a gasoline mixture, and we're looking at droplet radius versus time. If I squared this, you would see something that looked like the d-squared law. It doesn't show up very obviously here, but the vaporization or the lifetime of the droplet, the vaporization rate is slightly faster when we include the UNIFAC effect. And that's explained by this plot. This shows the boiling temperature as a function of the amount of ethanol in the gasoline mixture. And as you can see, if I had only ethanol, I would have a boiling temperature of about 78 centigrade. And I'm sorry, this was not gasoline. What was that? Well, we had a single component, and I can't remember what it was. Something with a boiling temperature of around 60. Anyway, it was probably pentane, somewhere around there. So pentane ethanol mixture. If you had a standard model, you would basically, as you increase the amount of ethanol, see a linear increase in the boiling temperature. But with the UNIFAC model, you see that there's an interaction between the polar ethanol and the non-polar pentane, which depresses the boiling temperature significantly over a wide range of ethanol content. So because you have the lower boiling temperature, you have the faster vaporization and shorter droplet lifetime. I'm just showing you the 10% ethanol point here. That's this one over here. But you would see significant differences if we had run with more ethanol in this calculation. So that's the effect of this non-ideal vaporization. And that shows up when you compare, now this is actually gasoline, results with and without the UNIFAC model, looking at the distillation curve of gasoline. So if you look at temperature versus the volume distilled for gasoline, this is the experiment. This dotted line is for pure gasoline. As you add more and more ethanol, you see that you basically, the distillation follows pretty much what you would expect for just the ethanol, and then at a certain moment, depending on the ethanol concentration, you catch up to the gasoline curve. If you didn't have the UNIFAC model in place, you'd see a very different set of distillation curves for different ethanol concentrations as seen with the UNIFAC model in place. And in fact, if you look in detail, you can see much closer correspondence between the various ethanol concentrations when the UNIFAC model is used. So basically, the boiling temperature depression seen by adding ethanol to gasoline is just ignored when you don't use this activity coefficient in your simulation. Okay, I'm going to take our next break now, but when we come back, we're going to discuss realistic models for multi-component fuels and the vaporization. Questions, though? Anything quickly? I'll take more questions at the end of the break. Okay, so we'll meet back in 15 minutes.